Hello level 2s again, and welcome to 2.4 Atomic Structure and Bonding, and this is lesson 4 on polarity. So here are our two learning objectives. We're going to define polar and nonpolar bonds, and then we're going to justify why a shape is polar or nonpolar. So here we have three pictures of types of bonds. So two of them are covalent, which means the sharing of electrons. So this is a covalent and this is a covalent, and this one over here is an ionic because it's where a complete transfer of electrons have taken place. And we're not worrying about ionic today. Today we're purely focusing on our covalent bonding. So there are two types of covalent bonds. One is nonpolar and one is polar. So a nonpolar covalent bond is where you have the same atom sharing electrons, and it's really important that it's the same atom, and that's because these atoms, or the nuclei of these atoms, are going to pull these bonded electrons exactly the same. Okay, so a nonpolar bond is one where there are the same atoms bonded together sharing electrons. So a polar bond then is where one atom pulls the electrons slightly better than the other, and this only happens when you have two different atoms. So you can see here we've got chlorine bonded to hydrogen, and chlorine in this case is pulling the electrons in this bond slightly closer towards itself. And because the electrons are sitting slightly closer, we say it's slightly negative, the chlorine, and the hydrogen slightly positive. So what causes this of one atom pulling the electrons in a covalent bond more than the other? And the term is actually electronegativity. And you don't have to learn the entire trend of this year. That's a level 3 concept, but you do need to understand some of it. So electronegativity is an atom's ability to pull on a bonded pair of electrons. And the most electronegative atom is fluorine. And so we just get you at level 2 to remember that trend, that it increases towards fluorine. So fluorine's the most electronegative, okay? And then it goes oxygen, and then it goes nitrogen, Fon. Okay, so fluorine's the most electronegative atom, okay, and anything near fluorine is going to be high in electronegativity, and it means they're able to pull those bonded electrons closer towards them. The why of that is actually to do with the number of protons in that element's nucleus and the size of the atoms. Those are principles that you learn at level 3. If you're interested, I can explain those to people, but however, you just need to know for level 2 that electronegativity is an atom's ability to pull on a bonded pair of electrons, and fluorine's the most electronegative. Okay, so just to recap, a nonpolar covalent bond is when electrons are shared between the same atom, or element I should say, and a polar covalent bond is any bond where two different atoms are sharing electrons, because one will always be more electronegative than the other. So we already know what covalent bonds are, sharing of electrons, and we know that it's between two non-metals, okay? But remember when we spoke about types of bonding in chemistry, I said to you that you could always describe every bond as electrostatic. So the electrostatic attractions here are between the positive nuclei and those negative shared electrons. So that's the electrostatic attraction of a covalent bond, okay? So electronegativity we've already spoken about, and we said that fluorine was the most electronegative. A guy called Linus Pauling came up with this scale, and you don't need to memorize this scale at all, but it is a lovely little scale which shows us the varying levels of electronegativity. And you can see here Fon have the highest. Okay, you're probably like, oh my God, chlorine's got 3 too, so which one out of these two? And I always say nitrogen because it's smaller. Okay, so we've been through nonpolar, it's when it's the same atom, and we've been through polar, when it's different atoms and it causes the electrons to sit closer. So if we were doing HCl like the example shows, I often draw the electrons in the bond slightly closer towards the chlorine atom. So that gives it a slightly negative charge, and hydrogen a slightly positive charge. This charge separation is known as a dipole. Okay, and that's really important. So dipole just means a separation of charge. Cool, so let's just have a look really quickly. Pause it for a second and answer these questions. Coolies, two different atoms, polar, same atoms, non-polar, same atoms, non-polar, same atoms, non-polar. Hopefully that makes sense. So bonding in chemistry, folks, is a bonding continuum, which means that, it's on like a massive scale, and we can use these electronegativity differences to kind of tell us whether atom or bonds are polar or ionic. If there's a massive difference in electronegativity, you're looking at an ionic bond, and that happens if we just jump back here. If you look here, an ionic bond is between a metal, so these parts of the periodic table, and a non-metal, and therefore because fluorine's the most electronegative, it has the highest numbers, and around them have the highest numbers, and so your metals would have the lowest numbers. So that would give a great electronegativity difference, and that leads to an ionic bond, complete transfer. Because if electronegativity, by definition, is an atom's ability to pull on a bonded pair of electrons, the greater the electronegativity means it can actually pull the electrons completely, and that makes an ionic bond. So what if there's a small difference that leads to a polar bond? So if we look at a bond between carbon and nitrogen, that gives you a difference of 0.5, polar covalent. If we're looking at a bond between phosphorus and sulfur, that gives you 0.4, a polar covalent bond. Now, when you look at the scale that I showed you, it's just an approximation. Kids can get really tied up with the values. So like, oh my God, anything that's less than 2 can't be ionic, and anything that's less than 0.5 can't be a polar covalent. It's not true. It's just approximate values. I just get kids at level 2 and level 3, to be honest, if they're two different atoms and they're both non-metals, then it's a polar covalent. If it's the same atom sharing electrons and they're both non-metals, then it is non-polar. And then I describe ionic as being a metal and a non-metal bonded together. There are exceptions to what I've just said, but we don't come across them at NCA, so you can just hold that fact true for now. Okay, non-polar shapes. So that's our main focus today. We've been learning about shapes, and so now we have to look at whether they are polar or non-polar. And it all comes down to whether they're classed as being symmetrical. Now, it's not symmetrical like in maths where you draw a mirror plane and you make it symmetrical like so. It's just where the bonds surrounding the atom, whether the dipoles that are created can cancel out effectively. And if we've got what we say to be a symmetrical shape, then there's not one side of the molecule with a positive charge and one side with a negative. And so therefore we say that the dipoles have cancelled out, and therefore the structure would be non-polar. Now, there are 3 shapes this year out of your 6 that are said to be symmetrical, and they are tetrahedral, trigonal, planar, and linear. You'll probably make the connection straight away that these are your parent geometries. So your parent geometries are said to be symmetrical, and if all of the atoms surrounding them, so if we were looking at methane, for instance, if all the surrounding atoms, so I'm talking about these, are identical, then they will be non-polar. If they're not identical, then that's going to change, and we'll talk about that. So this is not going to be non-polar, but we'll get to that. So here are some non-polar shapes. So we've got linear here, 2 electron density regions. Okay, in this linear shape, you've got a CO polar bond because they're different atoms, they're both non-metals. Oxygen's more electronegative than carbon, so that would be slightly negative, that would be slightly positive, that would be slightly negative, that would be slightly positive. Okay, we say this shape is symmetrical. Therefore, these dipoles that are created cancel out, and your shape is non-polar. And effectively what we're saying is that there's not one side of the molecule that's positive and one side that's negative, and therefore we say it's non-polar. If we look at BF3, it's got 3 polar bonds between B and F. F is more electronegative, so slightly negative, slightly positive, slightly positive, slightly negative, slightly negative, slightly positive. And so these dipoles can effectively cancel out. There's not one side of this molecule that's positive and one side that's negative, and that's because of the symmetry, or we call it a symmetrical shape. Okay, so you can see that all the negatives are on the outside and all the positives are on the inside, so it's not one positive side and one negative side, and therefore we say that the dipoles have cancelled and it's non-polar. Let's look at this one here. Chlorine's slightly negative. It's closer towards fluorine, and the carbons will each be slightly positive. So we can see that there's not one side that's negative and one side that's positive. So we say this structure is symmetrical and that the dipoles have cancelled and it is non-polar. Okay, now we don't do vectors in NCA. Vectors are these lines which show the direction towards the more electronegative atom, but it can be quite useful to see, to explain this at times. Okay, so all of these shapes are classed as being symmetrical, their dipoles cancel and they're non-polar. Please be mindful, you will not achieve this question if you say that the bonds cancel, because the bonds are not cancelling, it's just the dipoles created from the bonds which are cancelling. So here's a template answer that you would use. I actually hate this shape here because what tetrahedral looks like that, we know that it's straight, solid, dotty, even though I'm hideous at doing this with these pens on the screen, but this is what that shape looks like, okay? So we say this is how you would answer this question. We say that there are 4 CCl polar bonds because chlorine is more electronegative than carbon. Okay, that should just be carbon. I'll change that in your notes. The tetrahedral shape is symmetrical, okay? So therefore the dipoles cancel and the shape is nonpolar. It's as simple as that. We don't need to get waffly. We've stated the type of polar bonds that are present. We've stated why that they're polar. We've stated that the shape is symmetrical, the dipoles that are created will cancel, and it's going to be non-polar. So hopefully that makes sense. Kids try and make these answers so complicated. Keep it really simple. So polar ones then. So polar is when the atoms are not symmetrically arranged. So they're either not symmetrical or asymmetrical. And the 2 shapes that we have, which are actually 3 because there's 2 different bents, but any shape that has a lone pair, which is trigonal, pyramidal, bent, will, no matter what, they will always be polar because they're always going to be asymmetrical. So it's a really important thing to know. So any shape with a lone pair will always be polar because they're asymmetrical. Okay, so this means their dipoles do not cancel and therefore they are polar. Okay, so the other time that you can have a polar shape is what I was saying before. If you have a shape where all the surrounding atoms are not identical. So CH3Cl is an example of this, and that's because this dipole and this dipole will be different, so they won't actually be able to cancel. Okay, so the rule with polar shapes is that if there's a lone pair, they will always be polar. And then the other side is that if you've got a symmetrical shape, so this is tetrahedral, it's symmetrical, but one of the atoms is different to the others, then they will be polar as well. So here you can see, folks, that you've got 3 NH polar bonds because N is more electronegative than H, okay? And you can see that when you put in all the dipoles, the N ends up positive and all the H's down, the N ends up negative and all your H's down here are positive. So part of your molecule is negative and part of your molecule is positive, and overall it is said to be polar. And if you look at water, okay, you've got 2 polar OH bonds because O is more electronegative than H. Okay, and you can see here that if you look at that side's negative, that side's positive, so therefore the dipoles cannot cancel and therefore that structure is polar. Okay, so again, we don't have to do vectors at level 2, but they're quite useful in seeing it here, that you can see that these have got a net dipole in one direction, and that's why they're polar. So we can explain this quickly. Here's your template answer. We state about why the bonds are polar, and in this case, oxygen's more electronegative than hydrogen, and we state the number of the bonds. Okay, we just say that the bent shape is not symmetrical, the dipoles do not cancel, and the shape is polar. Okay team, so I'm just going to pause there and I'll start part B of the video very shortly, not much to go.